Hello and welcome once again for another ES340 video. Today is day 21, part B. Okay, so we left off last time discussing the design of vapor compression systems. However, the vapor compression system has to have some kind of working fluid. Now, as I think I've already mentioned earlier in the course, because I wanted to highlight how certain people are thinking about the future of, say, heat pumps and stuff. There are techniques that are available that do not require the use of a working fluid. You can have a fluidless type system that moves heat around with electrical elements, and there are advances being made along those lines all the time. So potentially one of you engineers may go off in the future and do so, make these kinds of improvements. But for right now, the most common type of refrigeration system uses a working fluid, and the working fluids are chosen for a variety of reasons, right? Obviously, that you want them to operate in a proper range, so that you don't want them to be corrosive. You want them to operate over a certain range of temperatures and pressures that would be acceptable for the various parts, the compressor and whatnot. So you don't want them to require too high of pressures in order for the system to operate with that high efficiency, because the compressor is only going to be able to go be able to work in certain regions of pressure itself, and things like this. And also, you also don't want the temperatures that are involved necessary to be too high or too low and things like that, right? So there's a lot of things that go into the choice of refrigerants. However, refrigerants that were popular in the 1930s, when we first started revolutionizing the refrigeration industry, were what are called chlorofluorocarbons. I'm sorry, and there's also hydrochlorofluorocarbons um, that were used commonly during that time period. Now, I don't want to get too deep into the weeds of saying, oh, this was bad or whatever. I think that it was a good thing that we moved from requiring large blocks of ice or whatnot in order to develop these refrigerators that you could just plug into an outlet in the wall. That was revolutionary, and changed the lives of many people. But as we discovered later, those the chlorofluorocarbons, were bad environmentally. They're often called freons. That's the trade name that was given by the company that was making them, DuPont. And the refrigerants actually have multiple environmental hazards associated with them, but a primary one that has come to mind in recent times is global warming. So when these things are released into the environment, they act as traps for heat energy coming from the sun, and some of them are very efficient traps, such as the DuPont actually named these refrigerants based, rather than having to go through the chemical formula that was used. They just gave them names starting with R, in order to simplify their system. So DuPont started, with, say, R12, R11, R22, R134A, which is what you've been what we've been discussing a lot in this course, because that's a commonly used one in more recent times, is R134A. Not to say that there aren't others, but it's a commonly used one now. But obviously, we would like to take into account the warming potential of these gases that might be leaked into the environment. And as I mentioned, there are other environmental hazards associated with these refrigerants. So we have to keep those, that's another factor that we have to keep in mind when we're choosing such systems. And maybe that's an argument for trying to move away from refrigerants and into something that doesn't require a refrigerant at all, because obviously if we could get similar efficiencies in systems that don't require a working fluid, that would be an amazing advancement for society. Okay, so commonly used ones were R12, R11, R22, and so on. I think these were commonly used in the decades following the 30s. And then commonly used today, not that there's not others that are used. As I mentioned, there are others, and you can go take a look. But commonly used today is R134A. Okay, which is why throughout much of the course, we when we did examples with refrigerants, we used refrigerant 134A, because this is something kind of relevant to modern day applications. I guess it's a lowercase a. Relevant to modern day systems. And also R22 so this is in refrigerators. But R22 in AC units. But this is getting phased out. So obviously now that you get into actually doing things as an engineer, you can't you do have some restraints, right, on the things that you can use, materials and such. So regulations, this is a regulatory phase out. Regulations actually do play a role in an engineer's life. However, that does allow for innovation, right? As I mentioned, now we actually are getting to a point where we are having designs that don't require refrigerants at all, and this is probably what the future is going to look like, if I had to guess. But in any case, as you can imagine, then when we do example problems and whatnot, we're probably going to deal with refrigerant 134A for that specific purpose. So that gives an idea. In these vapor compression systems, that's typically, particularly refrigerators, that's usually what is used when in modern day applications. One final note that I'll make, and then we can end this video, is that There are other refrigerants that are called natural refrigerants. Natural in the sense that they're naturally occurring, not something that needs to be largely produced in a lab or anything. And this includes ammonia, which we've seen some stuff where we've dealt with ammonia, methane. By the way, ammonia actually has its own number. So in the numbering system that was used by DuPont, ammonia has its own number as well, because why not, right? This just simplified everything for the company. Methane has R50. Methane actually is produced in large amounts in our environment. Butane, R600. Propane, which is R290. These are natural refrigerants. However, these are not as widely used, although I imagine that with probably with the R22 phase out, they will be used more frequently. But ammonia is probably the most popular among all of those that are listed in cases that are using natural refrigerants. So there are options outside of these chlorofluorocarbons and hydrofluorocarbons. And these, by the way, as I mentioned, they're not only do they have global warming potential, I should mention this, they also tend to persist in the atmosphere for long periods of time, which means that the effects are long-lasting, which is obviously not ideal. And this is why we end up having to come up with engineering solutions to problems such as these. That's all that I have for this video. See you again soon.